bio readouts are all in the green. Looks like she's alive. There goes our salvage, guys.
Common gases in your life. This is a replacement for the labs we lost and an introduction to chemical formulas that are the main feature of grade 10 chemistry. My rationale for this: there is a series of labs that I cannot replace, and I don't have his video, and even so, it won't serve the function that it needs to. In grade 10, you will focus on reactions. In grade 9, we study gases and sublab activities and basic reactions thereof. I'm saddened that we can't do these as labs, but I want you to see these reaction formulas for the story that they tell. I also want you to be the best in grade 10. I want you to stride into that room like a colossus of chemistry, undaunted and uncowed, ready to face a hail of formulas and shelter all the others under the cape of your confidence. Yea, ye shall be a wise but gentle tutor to those that find themselves underneath thy wise vision-compassing brow. You need to describe the nature and effects of carbon dioxide, oxygen, and hydrogen. Explain the results of hydrogen combustion. Explain the results of hydrocarbon combustion, not mandatory. Explain the result of a metal dust explosion, and link combustion processes to decay and decomposition in ecology. Gas 1, oxygen. It's a diatomic element. Again, di is equal to 2. When you see CO2, you automatically say carbon dioxide. So you already knew. We say oxygen molecule to denote this. O is the element oxygen. O2 is the fact that it always comes out in pairs. You can do the Collotti notation, which shows the whole shebang of its formation. This notation, or the structural one. Sometimes these notations look like that, sometimes they don't. It's all the same thing. Oxygen supports combustion. Rust and decomposition can be called slow combustion. Our atmosphere is around 20% O2. A 100% environment, therefore, has 5 times the concentration of oxygen, and fire would be intensified accordingly. The traditional symbol for an oxidizer, that is, oxygen, or any other substance that acts like oxygen and will help a fire. Notice the letter O underneath the flame. I like to think of oxygen supporting fire. Alternatively, it looks like someone's head is on fire. This is a warning of an impending attack by Ghost Rider. And also why we put our hair up when playing experimenting with fire in chemistry class. Gas number 2, yay! Hydrogen is also a diatomic element or diatomic gas. It is a highly flammable gas. It is used as a fuel in rocket engines and had a brief history of lifting passenger blimps until helium replaced it. Helium, being a noble gas, is unreactive. It'll lift a blimp and not blow the blimp up. The shuttle carried hydrogen and oxygen in the large tank. They are mixed and burned in the 3 main engines. And again, you can draw hydrogen like this, or like that. This is not really given treatment till grade 11. In grade 10, they're still going to want to see Lewis dots. This is the burning of hydrogen when we wanted to burn it. This is the burning of hydrogen when we did not intend that to happen. So here's a perfect example of when a gas or an element or a chemical can simultaneously have a good and a bad feature. It's a great feature in a rocket engine. It's a terrible feature in a passenger blimp. Now, what happens when hydrogen and oxygen meet? Well, that's what happens. Hydrogen meets oxygen here, hydrogen meets oxygen there. But what happens chemically? Well, the hydrogens are going to approach the oxygen. Oxygen has 2 missing valence electrons, and hydrogen only has 1 valence electron. So it's either going to try to gain 1 and finish its shell of 2, or it's going to throw away 1 and empty its shell. So if we look up here again, they both want. So they both want to get 2 in their outer shell. This gives them 2 choices with oxygen. They could engage in a donation bond, an ionic bond to oxygen, and pass their electron forward. And that would be good, but we could also go for a shared bond. And the oxygen puts its 2 forward, hydrogen puts its 2 forward, this hydrogen claims to have 2, this hydrogen claims to have 2, and this oxygen now looks like it has 8. The question is, which one of these bonds will it do? In either case, what we're seeing is 2 hydrogens bond to 1 oxygen. Wait a minute, isn't that H2O? Yeah, it's water. It could form an ionic bond or a covalent bond, and its structural diagram that doesn't bother really showing you the bonds is written like this. What does happen in real life? It's actually somewhere in between ionic and covalent, which is why I would not ask you to draw water. But in grade 10, it's going to become the basis of acids and bases. Here is another way of drawing the water molecule. Let's look at this reaction by formula. We write H2 plus O2 creates H2O. These atoms never go out by themselves. This is something we sort of expect you to remember in grade 10 academic. We'll point it out more often in grade 10 applied. What it's telling you is hydrogen will react with oxygen to produce water. The conditions under which it does this is not implied by the formula. We don't know if we need to set it on fire. We don't know if it needs cold, platinum bedding, any sort of condition under which this reaction would take place. We don't know until we experiment. One of the things we want to make sure you don't write it as is this. H plus O makes H2O. No, 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 no. The cat. No, 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 no.
No, 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 no. Oh, no, 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 no.
Gotta write it this way. That means this vehicle is a steam engine. It's just making steam. It's the cleanest burning fuel that ever existed. There is hydrogen and oxygen in this big red tank, and it burns to form steam. That is definitely not true of these 2 engines. The third gas we want to look at is carbon dioxide. This is the Collotti notation that shows all the movement forward, and here are common notations you see online showing a covalent compound like CO2. A structural diagram I wish we would learn in grade school. Why they save that for the last and do these first, don't know. Typically, a covalent compound, they call it a molecule. I'm lazy with those terms, and a compound is supposed to refer to ionic bonds like salt. Some teachers are picky about that, I'm not. You know we breathe out carbon dioxide, but you may not realize it's an outright poison. It will kill you at under 10% concentration, and quite rapidly. Any combustion reaction that has carbon present will produce carbon dioxide and has the potential to kill. This means if you decided to do a swimming pool full of Coca-Cola and throw in Mentos, you could suffocate. The combustion process in your body is called respiration. That's how you produce CO2. You are oxidizing your food. Enough people in a room and you will suffocate from the CO2. The natural gas to your home is called methane. It also is used in the Bunsen burners in the school. I covered in detail in my hydrocarbon combustion videos. It's mandatory in grade 10, but I prep you with it in grade 9. We don't need to look at the details here. You can go to the video in the links to see it in more detail if you want to be really ready for grade 10. This is the formula for methane, and here is oxygen. They will combine to form CO2 and H2O. If I draw them out structurally, right, this would be represented by 2 electrons here, 2 electrons there. You can pretty much see, oh yeah, an oxygen is going to go scoop up 2 hydrogens to form water. And there'll be more water formed here, and a carbon can bond with 2 oxygens to make CO2. If I just wrote a list of C, H, and O on a sheet of paper and asked kids to make a formula, even in grade 3, most kids could go, I can make H2O. And another kid might go, hey, I know about carbon dioxide. It ain't rocket science here. But now we have a combustion that is producing a potentially deadly gas. And that's why it has to be vented. Metal fires are a little bit different. They won't produce CO2 directly. Let's look at 2 elements that we're familiar with, iron and magnesium. And you can see how they could bond with oxygen by passing over the electrons to form iron oxide or magnesium oxide. Iron oxide I covered in my crystal chemistry. Here is an excerpt from that same slideshow. This would be a grade 10 question. I tell you I want you to make iron 3 bond to oxygen minus 2. And you'll have the 3 electrons here, the 2 electrons there, and you can go through that video and see the steps to get to here. You don't need to show me that in grade 9, that is grade 10. That would be one version of iron oxide. The other version is even easier. If there's only 2 electrons, then it's just FeO. The weird part is, iron can combine in 16 different ways with oxygen because chemistry ain't finished for you yet. There's way more to go. There are more bonds out there than ionic and covalent. You know iron oxide is rust, typically this color. But there are 16 kinds of iron oxides and hydrates that can be used as paint pigments. When you look at a rusty wall like this, you are seeing a mixture of all the different valent states of iron plus attachments to water. So there's chemistry visible to you here that is much more complex than what you've studied. You can understand the standard black iron oxide and the red iron oxide. The rest, those iron oxides are more complex chemistry. And this is a picture of rust. It's not moss on a rock. We get into a little bit of trouble with the terms rusting, oxidation, combustion, and decomposition. Combustion is usually regarded as the presence of flame. Rusting is called oxidation, slow oxidation, or slow combustion. There's kind of a vagueness here. Decomposition is a term that adds further trouble. It has a highly specific meaning in chemistry for grade 10. But in ecology and in plain everyday life, we mean rotting when we say decomposition. And rotting is often a combustion-like process. All of you know about photosynthesis, the making of oxygen from carbon dioxide that plants do. What we do is called respiration. We use oxygen to take sugars and convert them into energy and carbon dioxide. You do respiration, and so does a compost pile. The little organisms that cause decay are mostly animals, so they breathe oxygen and breathe out CO2. This means digesting food, burning food, composting food, rusting metal, burning metal are all a form of combustion or oxidation process. This is burning magnesium. This is how planes try to distract heat-seeking missiles. And what I see is that, firing their flares to distract heat-seeking missiles. If you ever fire a flare on a boat to get attention, you're looking at a magnesium fire. That's the formula come to life. This one is iron being set on fire. When the grinding process gets so hot, the iron ignites and catches fire in the air. If you have a shop class or a grinder somewhere, look on the ground. There are no sparkly metal pieces. It's rust that hits the ground. The iron is fully combusted or oxidized in the air, and you don't find metal particles on the floor, you find rust. And you could actually sweep it up and turn it into paint if you wanted to.
You know, almost a foot long, even though I'm only going to cut about 2 inches right now. So let's go ahead and fire this thing up, and we'll do some cutting. Okay, now with thinner material, this is 1/8 inch material. With thinner material, I've got a different technique I'm going to use, because I want to put a slight bit of travel angle on there, like a little bit of a push angle, and go across that way. If I go straight up and down, it's liable to weld itself back together. Okay. So this way I can blow that material across. So I'm going to go ahead and just get into position, get comfortable. I'm going to get the piece up to the kindling temperature. Okay, this right here is like a kindling temperature. Once it gets that glowing red, okay, that's what I'm looking for. I'm going to do that right there on this side of the line, and then I'll hit that oxygen lever all the way. When I do that, you don't want to just ease into it. With this thing, with the oxygen, it's all or nothing. So push that handle all the way down. Okay, right where I need to be, hit the lever. And cut right across. Alright, so there's that. Hopefully that helped.
Here's what you look for on the edge when you see how that molten puddle starts right there. You want to do it like right before that, or right when it first happens. You can't see it here, but I'm waiting till I see a little tiny speck of molten, then I push the oxygen and then just drag it straight across. I can't really tell you the speed to go. You have to practice, but you'll get it after a little while. It's not really that hard. You want to just keep the fire right on the edge, and just, it's hard to explain, but you'll get it. It's just the basic.
Now you're getting some eyesight. The experiment we couldn't do was setting fire to a bunch of metals, but you've all experienced it anyway. All this beauty is the combustion of metal compounds. The yellow of sodium, the purplish of cesium, the green of copper, the ruby red of strontium, brilliant white of magnesium, and the sort of, I don't know, colorblind guy color of zinc, and purple for potassium, and barium. All of this you can see now when you look at the sky. It doesn't take away any of the majesty of these fireworks, it makes them cooler to understand this is the applied chemistry you're seeing going on here. And this is the lab I'm so sad we couldn't do. But your new eyesight goes further than this. Way further. We can take this and aim it at the sky. There's giants out there. Just look at this thing. He's got a popped out eyeball, tall head, a mouth just roaring like Galactus, and he's giving us the finger. We aim our cameras at the stars, and just like the fireworks, these things are screaming out in their light what they're made out of. And because of the unique chemical light signature of each element, we may never reach these stars, but we know more about them than the bottom of the ocean because the light they're sending us tells us every last thing we need to know about them. From the pillars of creation, great lagoons of light paint the night sky in crimson and greens and blues, fiery explosions, as surely as the stars orbit each other and planets orbit the stars, electrons orbiting their nuclei leap merrily back and forth, releasing pulses of light that characterize each element, each compound in existence. There is nothing that we can see in space that does not tell us its unique signature of what it is composed of. What the hell is that thing?